Giving us a second lecture on scattering theory. Take it away, Sebastian.
Okay, hello. How are you? Morning. Are you happy today? More happy than yesterday? Less happy? Yes. I hope that the slightest thought about learning some S-matrix theory makes you happy. So I'm here to provide some happiness for you. Okay. I need some white chalk. Okay, let's start. So this is lecture 2. Let me just remind you again, this is my email address. If you need it for anything. So, lecture 2. A short reminder what happened yesterday. We learned a little bit about lattice QCD, or actually just QCD at first, effective field theories, and there was some very broad surface level introduction to S-matrix theory. And as Andrew mentioned yesterday, so these are all tools that you want to use to understand QCD, or strong interactions. Okay, so that's important to remember, is 3 things can complement each other and help each other out. Probably lattice QCD is the most rigorous tool we have for studying strong interactions. It doesn't mean that we cannot learn a lot from these two other techniques. And the S-matrix theory that I will start talking about today is, as I said, based on some very general principles. That will help us constrain models of scattering amplitudes. And now, important point that I was trying to make was that amplitudes will be considered as some complex functions. Complex functions with interesting singularity structure or analytic structure. Okay, so I promised you that lecture 2, which is now, will talk about causality and locality, some of the principles and assumptions about interactions, and how they may be thought of as equivalent to analyticity of these complex functions. I write equivalent and put the question mark here because the equivalence can be proven to some degree in simple cases. In general, it has to be assumed, it cannot be proven, especially non-perturbatively in some quantum field theories. So, and especially relativistic quantum field theories. So, but we will assume, for the sake of convenience, that this equivalence holds in a strong sense, sort of in a sense that our favorite physicist from yesterday, Chu, would call maximal analyticity, or in other words, that functions are analytic up to certain singularities that are imposed by the physics. And I mean the physics. So I mean that singularities of these complex functions will be equal to some interesting physical effects. Okay. Now, as I said, this topic can get extremely complicated, especially if you want to study things at high generality, etc., non-perturbative, relativistic field theories. So today we will talk about this concept of this equivalence in very simple context, which will be first as classical mechanics. So this will be our example number 1. Then we'll talk about something like electromagnetic scattering. So it will have a little bit of relativity. And then we'll talk about non-relativistic quantum mechanics scattering. Probably, if we have time, we'll talk about 2 examples, A and B. Whatever A and B means, that will be clear later. And if you behave well, we might even talk about relativistic scattering. Okay, so goal for today is to understand this relationship. And what we will use, so the central tool for discussing analyticity is one of the most beautiful theorems of mathematics and of complex analysis, which is the Cauchy theorem, which I'm sure you all know. I'll just write it down. And this is not exactly Cauchy theorem. Cauchy theorem says that if you have a contour and you integrate some analytic function over a contour, and inside the contour there are no singularities, the integration is 0. But that essentially follows from that fact. Yeah. Sorry? Very good. As we saw yesterday, I'm very bad with putting primes on things. Okay, so we'll try to build intuition starting from simple examples, classical mechanics. And by the way, I need to mention that those examples are based on a book by Brazilian legend on dispersion relations, Nussensweig. I think I wrote it. Sorry? The father, yeah, the senior, Nussensweig. Yes. So nothing that you learn here will come from anywhere outside of Brazil. So. So details, unimportant details. Okay, so the classical mechanics example will be the model of Lorenz's model of refractive index. Essentially, the model is we have some medium composed of atoms, there are electrons flying by, and then there's an electromagnetic wave that enters this medium, and some of the wave gets absorbed, some of the wave gets reflected. It's probably something you might have studied during your undergrad courses. So essentially, it's a model where we have an atom and an electron, some positively charged object or negatively charged object on a spring attached to an atom. And then we'll try to understand what happens when some wave enters and interacts with this system. So mathematically, it's your favorite differential equation known as harmonic oscillator. So you're trying to study the motion of this electron, adding some dissipation, energy dissipation. There should be plus, I want to get it right. Zero. Okay, so this is the homogeneous harmonic oscillator equation if we don't include any driving force here. So the system is, imagine you have a medium of some nuclei, and then there are charged particles attached at springs to this nuclei. And then there will be an electromagnetic wave that interacts with the charge and sort of drives this oscillatory motion there. And some of this wave will get absorbed, essentially due to this dissipation here. Some of it will get deflected. I mean, we are not really interested that much in the actual system. Suppose you didn't come here to learn about refractive indices, but relativistic scattering theory. What we are interested in is studying the causal properties of this simple harmonic oscillator differential equation, again, in mathematical terms. Okay, so everyone knows how to solve this equation. We write the solution as some composition of positive and that's, I guess, my notation, and negative frequency waves. And you plug this here, you get the characteristic equation. I guess you're all familiar with that. And of course, you can solve this equation. You get the solution for the characteristic frequencies. Okay, hope that looks familiar. Let me point out an important fact. There's this negative imaginary part in the solution, which means that if we plug it here, the solution will decay exponentially, and that's because of energy dissipation. That's easy. Okay, so now what we do, we turn on electromagnetic wave. Essentially, we include here Lorentz force. There will be some time-dependent electric field. And I think for simplicity, we'll assume it's some basic oscillatory electromagnetic wave. So what is the what is the general solution of this problem? Harmonic oscillator with driving force. No, I don't think so. Oh no, I think you're, are you right? Yes, they have plus and minus sign here. No, I think it should be minus, right? Right, let me think. Oh. Yeah, oh my goodness, I don't see it immediately. Yes. Yes. But let me just make sure. No, yes, I think it's correct. I mean, the quickest way to see it is without thinking about math. Is we know that if gamma is positive, this is a system that loses energy. And if I plug this here, that's what happens. So no need to remember math. Okay, now if we plug this solution here, we can write essentially based on Fourier transform arguments the general solution as, sorry. I need to speed up. This form. Again, this is essentially taking a Fourier transform of this differential equation and speaking in mathematical terms, solving for the Green's function of this differential equation. And I'll just skip immediately to the solution. I guess. So this is a function that relates some energy mode of the incoming wave to sort of Fourier transform of the displacement of this charge. Now, important thing to notice is that it has this complex poles. And another connection that might be sort of interesting to you is that it's very similar to the Feynman propagator in quantum field theory. If you just use the on-shell condition for if you use the definition of the square of the four momentum. This is energy, and then you can write it essentially as square root energy minus omega, energy minus omega p, E minus plus omega p, with some I epsilons here. So essentially you see it's a very similar structure if you treat frequency as energy, and this is your pole in minus and plus. Okay. So, important thing to remember, this Green's function has two poles. Now, the general solution of the problem is given by sum of the solution to the homogeneous equation, which we'll skip, and the convolution of the Green's function with your electric field, the driving force. Okay, so essentially we can have many different energy modes entering the system, and then how it drives the response of this moving charge depends on the convolution of this driving force with the Green's function. Now, if we perform inverse Fourier transform, we'll see that this x of t, this integral is to plus infinity, again, the primes are correct. By inverse Fourier transform, mean that we write this Green's function in time variable as the omega. Okay. So now the question for you is, how one performs this inverse Fourier transform? So again, maybe I was going a little bit too quickly. Let me remind you, we're solving the general problem of some general incoming electromagnetic wave. This incoming electromagnetic wave can be composed of many energy modes. How they drive the system, this is given by integrating over all possible energy modes according to this equation. And if we want to study this response to the force given as a function of time rather than some energy mode, we need to perform inverse Fourier transform to get this Green's function as a function of time. So this is the integral we need to understand. How is this integral done? So we know what g tilde of omega is. It's here. Any immediate ideas? Sorry? Okay, yes, very good. We'll use Cauchy theorem. And Cauchy theorem up to some details. But essentially the point is we know that this is a complex function with two poles. We know the residue theorem, essentially. So we know how to integrate complex function by residues. And that's what we want to do. We essentially want to write a complex omega plane. We know the positions of these poles. Let's assume some value of gamma. So it will be at plus minus real parts, and it will have negative imaginary part. And now we need to understand what's the right contour to pick to perform this integral, right? Because you want the integral on the real axis. But now, typically, what one chooses is either large half circle in the upper half plane or large half circle in the lower half plane. The right half circle is determined by whether the function decays fast enough as the radius of the circle goes to infinity, because we want the integral over the half circle to go to 0, so this gives us the integral over the real line. Okay, and now the point is that whether this or that half circle is correct, it depends on the value of this difference t minus t prime. Which, by the way, I made a mistake. No one pointed out. There should be t minus t prime here. Because what will happen is, depending on whether this is positive or negative, we'll get some positive or negative decaying factor, exponential decaying factor on this large half circle. And depending on this, the sign of this object, we'll either have to pick this one or that one. Okay, so we have two cases. And I say that if we take t prime greater than t, we need to stick to this circle. So t prime greater than t means this is negative. And if t prime is positive, that means the opposite. And so what we observe immediately is that if t prime is greater than t, so this is negative, by Cauchy theorem, since we're integrating over the region of complex plane where there are no singularities, that integral evaluates to 0, right? And if it's the other way around, there are two poles, potentially the result is non-zero. So what we will see is that the result will be some Heaviside theta function times something. You can compute this something by doing this integration by residues. We can make an exercise. And this will be something that has this time decay factor in it, essentially responsible for the energy dissipation. So now the point that I want to make here is that this is a very general property of functions, the appearance of this theta function, functions called causal transforms. So causal transforms are functions whose Fourier transform is square integrable and up to some details, square integrable, and they are analytic in the upper half plane of the complex plane. So let me maybe write that down. They need to be square integrable, and they need to be analytic in what I will call I+. So I+ is positive upper half plane of the complex plane, I- will be negative half plane of the complex plane. Now why they are called causal? Because you can show, this is known as, I can never pronounce this name, Titchmarsh, or Titchmarsh, I will write it down, theorem. That this function satisfies these two conditions. Well, it must come with this theta function. Its Fourier transform will have this theta function in the result. But the fact that this theta function appears in the solution means that whatever happened before t does not contribute to this integral. So in other words, the effect of this particle moving on a spring cannot, or this particle cannot start moving on the spring until the force arrives and starts moving it. And that's what we will call primitive causality. Okay. We're very casual here, so casual transfer. Oh my goodness, that's my English. Forget about this. This part is correct. Yes, it's related to causality, not casuality. Okay. The Titchmarsh theorem actually states something stronger, although all conditions are equivalent, that the Fourier transform of the green functions vanishes for negative times. The energy Fourier transform is holomorphic. The upper half plane. And this is the part that interests us from the scattering theory point of view. This Fourier transform satisfies dispersion relations. And what are dispersion relations? These are relations that link together real and imaginary parts of Green's function, or the causal transform. And why are they important? Like from the point of view of this particular model, we know that, I don't have time to go into detail, but we know that the displacement of this electron can be linked with the dipole moment. Dipole moment can be linked to polarizability of the medium. Polarizability is linked to electric field by the refractive index. So if you replace X with P polarizability, G with N, the refractive index, you can essentially think of the Green's function in this model as a refractive index, complex refractive index. The real part of the refractive index is essentially responsible for refraction, bending the electromagnetic waves. The imaginary part of the refractive index describes absorption of the electromagnetic wave. So what does dispersion relations tell us is that these real and imaginary parts are closely linked together. This is a consequence of the fact that functions that are boundaries of holomorphic functions on the real axis are very special. They are constrained by the fact that they were holomorphic in the upper half plane and that they are these boundaries. So that means that absorption of an electromagnetic energy in this medium, in this particular Lorenz's model, cannot be unrelated to the refraction. These two phenomena are closely linked together. So this is the basic physics. Now, in terms of scattering amplitudes, there's almost exact analogy. Our scattering amplitudes, if we think about this frequency complex plane as energy plane, we will consider them as boundary values on the real axis as some holomorphic functions in the upper half plane. And the fact that they are holomorphic will lead to some relations that give us connection between the real and imaginary parts, and they are also called dispersion relations. Now, these dispersion relations can be used to model scattering amplitudes in some constrained way, because indeed these two equations are constraints of some type. Okay, so this was a basic example introducing you to the concept of causal, also known as causal transforms. Any questions? No questions. But note that when I mentioned causality in this context, I used the word primitive causality. Why did I use this word? Are there non-primitive causalities? Maybe ask me a different question. What is causality? Who wants to answer? So here I said, what we understand by causality is that whatever happened before the effect happened, before the wave reached our electron, it couldn't have moved, which means all the times before the motion of the electron cannot contribute. Sorry? Negative sign. Oh my goodness. This is a very good catch. There should be a negative sign here. This imaginary, I think we also can leave derivation of this dispersion relations as an exercise. This minus sign is important. Essentially, you derive these dispersion relations from applying or integrating the following function. And this minus sign comes from the I here, which I have no idea how you figure this out, because it's not very easy. Okay, our second example. Mm. When you talk about something like Feynman propagator, right? Because causality in quantum field theory means something different than primitive causality. So we slowly start discovering that there might be different causalities. How am I doing on time? Oh my goodness, extremely poorly. So let me skip electromagnetic wave. Let's jump immediately to the example from non-relativistic quantum mechanics. Okay, so during the online lectures, Lucas talked a lot about different simple models of short-range interactions. I want to sort of revisit that by studying a spherical wave scattering on some spherical well. So rather than having an incoming and outgoing plane wave, which you typically do in quantum mechanics courses, we'll simplify the problem. We'll have incoming and outgoing spherical waves, just to forget about angles for a moment. And you know that your Schrödinger equation, the stationary Schrödinger equation, can be written like this. Our wave can be written like that. So this 1 over r comes from the fact that we're considering the spherical. Scattering waves. Oh, I'm using minus here. Okay, I promised myself to keep h bar equal to 1. So this is Schrödinger equation where I set all the irrelevant constants to 1, except for this 2 for some reason. U is the depth of our potential, or if it's a bump, it will be the height of our potential. This S, I mean, we could write our solution in terms of two independent coefficients, A and B, but I defined the scattering matrix or scattering phase as second coefficient divided by A, so I pulled it out because we want to solve for that. Okay, and I suppose you know perfectly well how to solve this problem, so I'll just jump straight to the solution. I'll just write it down. Should be R here. Where this tank function is okay. So now, based on general considerations about Green's function of Schrödinger equation, we can infer that this S of P also is a causal transform. So in other words, scattering amplitude is also a causal transform. It's not a Green's function, but it satisfies these conditions. It's co-integrable, it's analytic in the upper half plane, unless it's not. What does the singularities of this object look like in the complex momentum plane? Okay, it's not immediately visible from the solution, but if we consider a bump scattering, so maybe I should use different color. That's a very good point, because there's actually a minus sign here, of course. Yes, this minus sign is important because, as I said, this S matrix is a pure phase. So essentially, this thing needs to have a modulus 1, and then we can write S matrix in terms of a phase shift, just like Lucas taught you. So that's why this complex conjugation here is important. Okay. So now let us think about what happens when we consider certain values of this U parameter that determines how strong the interaction is. So I claim that if we take very small u and positive, so u goes to something like 0, but from the positive direction, we'll have two complex poles at values that are given by, I mean, I can write it down. The real parts are given by k plus 1/2 pi. And if we start increasing the bump, they will start moving on these trajectories, the left and right. And there will be other poles that emerge and follow similar behavior. Okay? So this is if we have a bump rather than a well. Now, if we consider a well, then the poles, so now we consider a case where well is almost completely negligible, but negative. The poles also go to minus I infinity, but there are a position k pi. And then what happens as we start increasing, maybe I should write here, it goes to infinity. As we start increasing the strength of the potential, these poles will move to the imaginary p plane, and then they will split. One will start moving up, one will start moving down. And there will be a bunch of those. And at some point, at some interaction strength, they will start moving to the positive upper half plane of the complex plane, and some of them will be occupying the negative imaginary axis. So I told you that scattering matrix is a casual transform, so it should be holomorphic in the upper half complex plane. And, well, if it's not, according to the theorem over there, quantum mechanical scattering breaks causality. Does it make sense? So what's the problem here? The problem is that indeed scattering matrix is a causal transform, but we shouldn't be looking at the scattering amplitude as a function of momentum, but as a function of frequency, or in quantum mechanical terms, as a function of energy. So you're looking at the wrong complex plane. What's the relation between energy and momentum? Well, it's very simple. Or in other words, P is something like square root of E. Okay, so my claim is, if we look at S in the complex energy plane, it will be analytic in the upper half plane. Does it look immediately true? The question is how to convert from P complex plane by squaring to the energy plane. Well, if we have two complex numbers, Z1 and Z2, they are given by some polar representation with some two angles. Well, their product is product of magnitudes, but more importantly, the argument is sum of two phases. So if we take Z squared, which is Z times Z, we'll get something like E to 2I phi, where phi was argument of Z. So essentially, squaring means rotating the whole complex plane by the double of the angle. So this point will go to something like this point, where this is 2 phi. Okay, so what will happen to these poles in the complex plane? Well, they are at angle 90 degrees, so they will all go on the real axis. And so on. Let me switch from momentum to energy. What will happen with the negative real axis in momentum plane? Well, this is 180 degrees, So it will become the negative, or sorry, it will approach from negative half plane the real axis of energy. What will happen to the lower half plane? All this complicated stuff that's going on here, all these different poles for different cases, what will happen with them? Right? For example, these other poles that lived here, well, this is angle 270 degrees. If we take a double, it should move by 2 times 270 degrees, which is 540 degrees, right? Does it sound correct? Well, what will happen is we will notice that since momentum is a square root of energy, and square root is not a function from complex plane to complex plane, but is a function from complex plane to complex plane times complex plane, or complex plane squared. Or in other words, square root is a multi-valued complex function, right? We take square root of a complex number, we get always two solutions. So it's really a function from complex plane to complex plane squared. Or in other words, square root has associated Riemann sheet, which is the second complex plane. And we often draw it, I will try to draw it, although I'm not good at it. Often say that square root has a branch cut singularity somewhere in the complex plane. And through this branch cut singularity, we can sort of approach the second Riemann sheets that starts somewhere. And my claim is that all the poles that were living here will just move to the second Riemann sheet, second as complex plane associated with this square root singularity. So, in other words, what will happen is that all of this in the complex energy plane will disappear. But we will have to consider scattering function as a function on two complex planes. On the first complex plane, the only thing that will remain will be these poles at negative energy axis. There will be a branch cut singularity on the positive real axis. And through this branch cut, we will be able to access the second sheet where the scattering amplitude is defined. So this is complex plane number 1. This is complex plane number 2. And all this mess that was in the lower half plane in the momentum complex plane will become either poles on the negative axis here, or in the case of a bump scattering, poles in an upper and lower half plane that are complex conjugate of each other. And of course, this function will also has a branch cut. Okay, so this is a very simple model of quantum mechanical scattering. I claim that this casual transform, considered as a function of complex energy, not complex momentum. So again, it is holomorphic in the upper half plane, and it also is holomorphic in the lower half plane by so-called Schwarz reflection principle, has singularities that can be of particular type. It can be poles on the real axis, and this is what we call bound states, or bound state poles, because they correspond to the solutions of the Schrödinger equation with negative energy, right? These poles appear as singularities of the scattering amplitude at negative energy, and the singularities essentially correspond in the wave function picture to the process of the scattering wave function becoming from non-normalizable, normalizable. And that's how the singularities are, this physical picture, created. These poles that are partner poles of bound state poles in the momentum plane, we'll call them virtual bound state poles. Because these poles are almost bound if the interaction strength was strong enough to so-called support the binding. These poles would move through this complex branch cut to the first complex plane and would emerge as these bound state poles on the first complex plane. So these are almost bound, but not really. They potentially can become bound if we increase the interaction strength. Sorry? Yeah, U has to be attractive, which means there should be in minus here, yes. It's third minus sign mistake today. Okay, and what are these poles here? So these were corresponding to positive UKs. This is what we call resonance poles. So these are these famous resonances that I mentioned during the first lecture. I showed you a slide with different hadrons and said all these particles really decay, so they have finite lifetime. They are not bound states, as we can clearly see on this picture. These states will manifest in the scattering amplitude, which again, we consider scattering amplitude as a boundary of this causal transform on the real axis. So essentially physical scattering happens for real energies and doesn't happen for negative energies. So it really stops here. The presence of this bound state poles, so singularities on the second Riemann sheet, will be visible or will manifest in the scattering amplitude as bumps. Say if we have a sequence of poles, we'll have a sequence of bumps, but typically at one value of scattering interaction strength, there will be just one of these poles. And it will manifest as a bump with some width. This width can be related to the lifetime of the state associated with this pole. Now, can we associate particles with resonances? I mean, it's rather clear that bound states are particles. We can see them in detectors because they live long enough, or in principle infinitely long, such that our detectors can measure them. Now, are resonances particles if they correspond to some fancy complex poles? What complex energies really are? The real scattering, as I said, happens here. Well, that's a good question. I don't have an answer for you. Sometimes I think that they are real particles. Sometimes I think they are not. And the edge case for me is neutron. Is neutron a real particle? Well, it lives pretty long, like several minutes, but it decays. So in a scattering amplitude, it would correspond to a very, very narrow resonance pole. So resonance that lives very close to the real energy. And its width would be very small. So essentially, you'd see a pike-like structure. Yeah, there's a question. Okay, that's a very good question. Maybe we can leave this question for the discussion session, which should start now, essentially. Okay, so let me just finish, Andrew. Well, okay, so the main takeaway point is there's a deep connection between causality, either understood in primitive sense or, as I didn't have time to discuss, in a more sophisticated sense in the quantum mechanical systems, or even more sophisticated sense in relativistic quantum mechanical systems, and the analytic properties of scattering amplitudes or Green's functions, depending on the system. So if causality is preserved in your model of physics that you study, the S matrix, again, up to many technical details that are rarely proven non-perturbatively, it will be an analytic function in the upper half plane of energy. By something called the Schwarz reflection principle, you can also show that it should be analytic in the lower half plane. Okay, this depends on certain cases. And now, singularities that appear in these scattering amplitudes can be of several types. They can be poles that correspond to physical states like bound states. They can be poles that correspond to bumps in the amplitudes that create bumps in the amplitudes that we call resonances and that we measure in scattering cross sections. They can also be virtual state poles that are almost bound, but not really. But also note that there was this branch cut here. This branch cut told us that we need to think in a completely new way about scattering amplitudes as complex functions, that is, as objects that are defined of multiple complex planes, which we call Riemann sheets. The physical scattering happens on the what we call physical or first Riemann sheet, and it's a boundary value of scattering amplitude on the real axis. But there are important physical effects, just like resonances or virtual states, on these other complex sheets that can be observed experimentally. Okay, so as I said, as I wrote here, singularities, maybe even might see it, singularities are equal to some physical effects, and that's what we see here. We can represent singularities or physical effects in the amplitude as some singularities. What is the physical effect corresponding to the branch cut? That I didn't explain. This will be lecture 3. But I can tell you that branch cut singularities are of two types. They are either related to openings of new scattering channels, so situation when you have enough energy for a physical scattering to occur, or a new channel for scattering, for example, of two heavier particles to open, or these are so-called right-hand cuts, or there might also be left-hand cuts that are related to forces, which we could call, let's say, Yukawa-like forces. So essentially particle exchanges. Okay, so poles correspond to particles. Cuts will correspond to other physical effects that I will discuss tomorrow. Thank you.
All right, let's thank Sebastian. So now it's time for the Q&A. Someone had a question.
Yes, there was a question about what if a resonance appears as a dip.
Okay, you answer that.
So the case where this happens is this, in the famous case is for this lowest scalar nonet that I showed in like a dashed box on my picture. There is F0 500 or sigma resonance, which appears as a very broad bump in a pi scattering. So essentially consider pion scattering, and it can, what can emerge is also pion, Kaon, anti-Kaon, etc. There in this nonet, there's also a state called F0 980, which I think, as far as I remember, appears or is interpreted as a dip right below the KK bar threshold. So what happens there, as far as I understand, is that it's the threshold opening that leads to this dip. No?
If you had single channel scattering with multiple resonances, you have to have the amplitude come back to 0 and go back up in order for... So you
At
have to
channels, at thresholds.
No, for single channel scattering.
Oh, for single channel
Yeah,
scattering.
if you had multiple, so that's energy. You have a resonance, if you have another resonance, it has to come back down to 0 by, is it Levinson's theorem? Because the phase has to come back around for single channel scattering. The 980 is interesting because this happens right at the KK bar threshold.
Yes.
So there's multiple things going on.
Okay.
Because the KK bar threshold opens up, it doesn't need to come to 0. So what happens in pi scat, I'm going to erase some of this, sorry. What happens in pi scattering is you have the sigma, some broad thing, it dips, and then it comes back up. And this is where KK bar threshold opens up. So it already dips back down. So that's signaling that you're getting to the next resonance. But then there's an interplay happening here, so it doesn't exactly go to
Okay, so it's more complicated, than I thought, yes.
Yeah.
Essentially interference with another resonance and a threshold. Yeah, so what it means that a simple interpretation of resonances as bumps is not necessarily always straightforward or even true. Rigorously, resonances are, like rigorously in scattering S-matrix theory, they are defined as poles of the scattering amplitude, not as bumps. Bumps are manifestations of resonances, potentially, not always. You can have much more complicated structures in cross sections, as we will see probably in lecture 4. But typically, or maybe a good heuristics is when you're an experimentalist. I mean, experimentalists are much smarter than us theorists. For a very particular reason, they don't overcomplicate the physics that they study. They try to find the simplest explanation that works, and that's essentially how physics should be done. So when they see a bump, that's a resonance, that's a particle. And that works almost always, or surprisingly well.
I don't agree necessarily.
Okay, there is an ongoing controversy in like phenomenology, hadron phenomenology community, whether you can, how far you can go with fitting Bright-Wigners to everything. And well, I would say the people are divided to two camps. As a very abstract theorist who likes to think about poles and branch cuts, I should be in the camp where, no, Bright-Wigners are bad, but I've seen miracles made by experimentalists in their analysis with Bright-Wigners, so I'm just impressed by that.
All right, thanks. Are there any further questions or things for discussion? Yes.
Hi, thank you. I was wondering because why, so in the first case, and generally you find the poles of the Green's function, but there it looks like you found the poles of the S matrix, which you can relate, of course, but they're not equivalent.
Yes. So the point that I was making was, let me see if I can remember it. I mean, actually, I didn't make this point. That's what example 2 was for, that I had to skip. So let me see if I remember example number 2. The point was that if you assume that causality is satisfied by the incoming wave, so in other words, that you can create a square integrable A such that your wave function has a sharp front in time, so it is well defined when it arrives to the scatterer, then it implies that the outgoing wave also must have a sharp front, which means that this B coefficient must be a casual transform. But if A is a casual transform and B is a casual transform, that means that S is not necessarily a casual transform, to be completely honest, because it doesn't have to be square integrable, but it will be holomorphic in the upper half plane. So this was the example that I didn't discuss. This is no longer so simple in quantum mechanics, because you cannot create wave functions with sharp front in time. Essentially, the correct way of writing down this equation would be to write an integral over energy, because we are talking about casual transforms in energy. Oh, there should be P here still. No, yeah. It should be square root of E, I guess. And this should be considered as a function of E. The problem is that energy is positive. So integrate from 0 to infinity, not from minus to plus infinity. And it's impossible to build a sharp front of an incoming or outgoing wave function with a sharp front in time using just half of the real energy axis. Or in order to do that, you would need to consider energy eigenmodes of arbitrarily high energies contributed in order to build this sharp front. So the causality needs to be considered in a different sense in quantum mechanical scattering. That's why I called the classical causality primitive causality. So here, there are probably the most, I think, intuitive for me way to define causality in quantum mechanical sense. It has a name attached to it, which I never remember. So let me see in my notes. I can find it. As Schutzer-Thiomno causality. I'll just write down this name so you can look it up. Well, then Brazil made it to this lecture again twice, yes. So essentially, we need to consider wave packets that have some spread in time. They cannot be made into sharp fronts that arrive at the scatterel at well-defined time, and then we can see if the effect happens afterwards. We need to consider a wave function that has some spread in time, and we just say that the wave function, outgoing wave function at this space-time point cannot depend on the incoming wave function at, this cannot be produced for times larger than, or sorry, cannot depend on, oh my goodness, I'm speaking about 2 times. Essentially, this function cannot depend on the values of this function for times such that this t prime is greater than this t. No, less than this t. Okay. So now we're not talking about causality in a sense, like in a physical sense that we kick the ball and the ball moves. We're talking about some spread, this probability distribution at space-time point that cannot depend on the value of another spread probability distribution at the same time point at different time. So this is, I don't remember how this was called, if this was called, it has some special name to it, or just quantum mechanical causality, or Schutzer-Thiomno causality. And there is third sense in which even talking about wave functions is difficult, which is when you consider relativistic quantum mechanics, and then people talk about microcausality, which is defined in this very abstract way, that if we have actually, I sort of make an impression that this should be some kind of fields, this can be general operators, say, that this commutator of 2 operators at different, 2 field operators at different space-time points should be 0, or space-like separations. So that for separations that cannot communicate with speed lower than the speed of light. Which means that measurements performed at such separations should be independent of each other. So when we talk about proofs of analyticity of scattering amplitudes in relativistic field theories, most of those proofs rely on causality defined in this way, and some other additional assumptions about positivity of spectrum, Lorentz invariance of vacuum state, Green's functions, etc. And in certain cases, you can derive rigorously that your scattering amplitude should have a proper analytic behavior. Essentially, it's analytic in the upper half plane of the complex plane. But essentially, due to crossing symmetry, the amplitude can have additional singularities, so-called cross-channel singularities. Because here we talked about single variable, right? But we know that scattering amplitude, as we learned yesterday during exercises, depends on Mandelstam variables. Well, one of this is related to the other 2, so really 2 variables. So now we can complexify both of them and talk about 2 complex planes in S and T, or complex plane singularities in T for fixed S, singularities in S for fixed T. More general discussion, which leads to Mandelstam double dispersion representation, whatever. I'm just saying these words because maybe you want to look them up. And situation becomes more complicated. Crossing means that certain singularities that appear in the amplitude considered as a variable of T and U can propagate. This is not a very rigorous language, and can propagate to singularities, or can become singularities or manifest as singularities in the complex S plane. Maybe I'll talk about this a little bit tomorrow because it's relevant and important for dispersion relations. But here, essentially, yes, you have additional variables that we haven't discussed. We just talk about complex energy plane. In quantum mechanics, you could also talk about complex scattering angle, which we didn't get to. I mentioned we just consider incoming and outgoing spherical waves. But if we consider plane wave, then there will be some non-trivial dependence on cosine theta. We could complexify cosine theta and ask what are the singularities of cosine theta. Do they have any physical meaning? And the answer is yes. You can prove analyticity in cosine theta. You can show that singularities in angle, considered as a complex variable, also mean something physical. Okay, maybe I talk too much.
Actually, this is more like a comment, but it's also a question, because this naive question keeps in my mind. But you mentioned about the Breit-Wigner for resonances like the F0900 and 80. We usually use the flat T, but
oh yeah, flat T or
yeah.
flat T representation,
Yeah.
which is essentially what I would call coupled channel K matrix parametrization, where K matrix will be introduced tomorrow.
Yeah. But actually, my naive question is...
But don't get me wrong. You shouldn't use Breit-Wigner for sigma or F0. Definitely not. I just said that many cases when I would think experimentalists shouldn't be using Breit-Wigners.
No.
And they are using Breit-Wigners. And I think this is just forbidden. Like, they should go back to school. And they just show the results. And then I compare them to results of more sophisticated analysis that include complicated singularities, etc. And no difference. And then I think I should go back to school. So that was my point. The point that I was trying to make. Like in actual realistic applications, you should be always careful how you model resonances. Again, they are not always simple bumps, but simple bumps can take you a long way.
Okay, but this naive question keeps in my mind because I totally understand what you mentioned about the threshold on the pi scattering. What if we have a dip in after the threshold? You know what I mean?
A dip after the threshold?
Yeah, is there even possible?
Yeah, you can have very complicated structures that start existing when you have multiple thresholds opening up and multiple resonances. I mean, you can take a look at something like the pion-nucleon scattering cross-section. You just Google image it, which is my favorite thing to show because it shows a bunch of peaks and dips and everything like that. And if you count the bumps, there's like, on the order of 10 or so. And if you look at doing actual spectroscopy, finding out as much information you can, there's like, 30, 40 of them or whatever. So yeah, you can get very complicated structures, which makes our life hard as spectroscopists. You're welcome. All right, if there are more questions, maybe reserve them for the exercise session today. We have coffee break until 15 after. Let me remind you, for some who came in late, we have a sign-in sheet, which is a yellow notepad on the front table. Please sign in. We're going to have another one in the afternoon session as well. Thank you.